In this video, we're going to look at complex conjugates, and specifically complex conjugate pairs. And the reason we're going to dive into these is because we have essentially real valued problems that we're starting as our motivation here, these differential equations. And we're using complex numbers as a tool to help solve them. And yet somehow we have to end up with all real solutions. So somehow we're going through from real values to complex and back to reals. And that means somehow the complex numbers have to disappear before the end. One of the ways that happens is just naturally as we go through the calculation. We don't get random complex numbers, but rather we get complex numbers that appear in matching pairs. Those pairs have a specific structure to them. Here's the form right here. If we have a complex conjugate pair, if we have one of the complex numbers has a real component A and an imaginary component B, then the matching set of that conjugate pair has the same real and negative imaginary part. So the same real and negative, or flip sign is more accurate, flip sign on the imaginary part. Sometimes notation-wise, if we have a particular number already, a complex number, and we want to build the complex conjugate, we indicate that with a bar over the z value here. So what that means, if we have z is equal to a plus bi, then if we draw z bar, we would flip the sign of the imaginary component. So just to get some quick examples on the table, if we had 3 plus 2i, then 3 minus 2i would be a complex conjugate pair. So complex conjugate pairs here, and not those. Let's just some other ones like minus 5, minus 2i. All we have to do is flip the sign here, so we might start with a negative, and that's fine, and then flip the sign to be positive. Now, what would not be the case if we had minus 5, minus 2i, and we flip the sign of both things? In this case here, the real values are different, or the real components are different. And that's enough to break the conjugate pairness. So always the same real, always a flip sign on the imaginary part. Now, one thing that might be less obvious is if we took the number 3 and the number 3, so two all real numbers, but if we think of them as complex numbers, we can always add an imaginary component that just happens to be 0. Well, it doesn't really matter whether I add or subtract 0 of something, we get the same amount. So these are complex conjugates, but if we took two different real numbers, they would not be complex conjugate pairs. Now, those are sort of rare and trivial examples. Most typically, when we're working with complex numbers, we want them to be complex. We want them to have some kind of imaginary component, so we get these kinds of things. Other examples of non-paired would be totally different complex numbers like this. 1 plus 2i and 3 minus 4i, they are not a complex conjugate pair. It has to be the same real, same imaginary, but with flipped sign. Now, an example of complex conjugate pairs you have seen shows up when you look at the quadratic formula. Focusing in on the square root sign, we can actually show the quadratic form gives one of two real solutions, this two distinct real numbers, or a single real number repeated, or not just complex numbers, but specifically a complex conjugate pair. And again, this just comes from the b squared minus 4ac part here. If it is positive, then what we get is the square root of that some real number. So we can say let the square root of b squared minus 4ac equal some number. Let's call it k. Then your x is equal to minus b plus k over 2a and minus b minus k over 2a. And this is in the reals. This is a real number, and they're different because k is not equal to 0. Then we have the case where b squared minus 4ac actually equals 0 exactly. And if that's the case, that whole term disappears, and your x just equals minus b over 2a and plus or minus 0. So that's where the duplication comes in. We often call this a double root, but there's a solution which is, again, all real. And then we have the last case where b squared minus 4ac is negative. And so we have a negative underneath the square root sign. In that case, let's give this a name here. It's negative. We'll pull that out as a separate negative property. And then we'll have something, let's use k, let's use m, just for variety here. And m is positive and real. So the negative part gets factored out with the negative there, And so in that case, we have x equals minus b plus or minus the square root of negative m all over 2a. Again, just replacing this expression here with minus m. We can factor out the negative of the square root. That gives us an I. So we're going to have negative b over 2a plus or minus I times the square root of m. Oops, also over 2a. And so we're going to get two values there. B over 2a plus square root of m over 2ai, and its matching version, the same thing with a negative. So b over 2a minus root m over 2a. And this pair here, that combined with that, is a complex conjugate pair. And so we've seen this before, and again, it's this tie-in for equations that are fundamentally real. As we work through the solutions, when we see some kind of aspect of the solution or part of the solution, it typically, not always, but typically ends up having complex conjugate pairs appearing. Since we've been looking at geometric interpretations of complex numbers with the real axis here and the imaginary axis up here, it makes sense to look at complex conjugate pairs and see how they're arranged on the complex plane. So 3 quick examples. 2 plus 4i. 2 plus 4i is up here. We would typically draw that as a vector like so, or as a point, whichever way you want to think of it, and that would be z1. And its complex conjugate partner would be 2 minus 4i, and lo and behold, it has many similarities, has the same real component, but the imaginary component is flipped. So the geometric consequence of that is that we reflected it across the real axis here. And does that happen for all these cases? Of course it does, because we're only ever flipping the sign of the imaginary part. If we had negative 3 minus I, that would be down here, like so. And then minus 3 plus I, it's match set, again, simply reflected across the real axis. And if we happen to have an all real value, like here, 1 plus 0i, well, that would be here. And then if we flip that, we just get to the same point again. So these are complex conjugates. There's just not a lot of flipping that's visible. We end up exactly where we started. So flipped or reflected across the real axis. That's the structure that we get in this particular instance. A natural follow-up question is, what if we represent our complex number using polar form instead of Cartesian? Well, now we know the relationship's the same. We're going to be flipping our vector or our complex number, whichever way we think of it, across the real line. But now we just have an angular representation. So imagine we have pi over 4, that's 45 degrees. And we have length 4, so that would be about like that. That would be our z value here. Well, if we reflect that across the axis here, we're going to get the same length as before. And what's going to change? Well, we're going to have a negative version of the angle. It'll be negative pi over 4 as our angle. So in this case here, we write this as z bar. The complex conjugate of z is going to be 4 length with an angle or argument of negative pi over 4. So I'll highlight that negative part there. Negative pi over 4. Because of the way we defined our real line as the 0 angle, the reflection here, or complex conjugate pairs, just requires flipping the sign of the angle. Sign of the angle for polar forms, which is lovely. Very simple again. If we have an angle of pi over 4, if we reflect it, all we do is make the angle negative. If we have a negative angle to start, we make it positive. Now, the motivation for looking at these complex conjugate pairs was that they have some nice relationship to real values, and specifically what happens when we look at sums of them to start with. If we take a sum of these two numbers here that are complex conjugate pairs, you'll notice that we get 6 minus 2i plus 2i, well, that's plus 0i, and that's 6. And that is all real, or has no imaginary component. So if we did some calculations and ended up with this complex conjugate pair, and the answer we were looking for in the original problem was the sum of those two values, well, we would have something that is all real, even if we use complex numbers along the way. Now, the same thing's true here for a simple value like 1 plus 1, remembering that these could be, if we wanted, to be defined as complex conjugate pairs, again, all real. And in general, if we have a complex conjugate pair, we're going to have a sum that gives us 2a. Then because the sign is flipped for the imaginary components, we're going to have plus 0i, which is just 2a, which again is all real and has no imaginary component. And that was a fun thought experiment. This doesn't happen as often, anywhere near as often. But if you imagine the differences between two complex conjugate pair elements, what would you get? Well, it turns out you get the opposite effect. Instead of being all real, when you subtract one from the other, you're going to have, let's do an example here with the general case. If we subtracted these two elements, this time the a's, the real parts, would cancel out and give us 0, and we'd end up with positive 2bi. So that's an all imaginary case. And this is much less frequent, much less common. So just a fun little sideline, but it's not the focus of what we're going to be using complex conjugate pairs for. Now, an important follow-up to looking at the sums of complex conjugate pairs, always giving us real values, is that we see the same pattern when we start to look at products of complex conjugates as well. This is a little longer to do in terms of calculations, but it is straightforward. We have 1 times 1, that's 1. Then we have minus 2i. This is just like expanding a polynomial. Plus 2i, just look for all the 4 terms, mix and match in each way that you can. And at the end we have minus 4, and 2 i's means an I squared. Now that is pretty simple because those two terms cancel. And then it's even simpler. This looks imaginary, but of course we know that the value I squared is just negative 1. And so this equals 1 plus 4, which is 5, which again is all real with no imaginary components. Then is that a pattern we can rely on? Let's do another example to illustrate first, and we'll see what happens. Minus 3 times minus 3 is positive 9. We're going to have minus 12i and plus 12i with a double negative. So we see that same cancellation of those I terms. And then we're going to have negative 4 squared is 16, and we have I squared. And yet again, absolutely, we have that I squared, which is real. It's negative 1. And that sum turns into 9 plus 16, and that is 25. Again, all real, no imaginary. Finally, we can take a look at the general case here. And if we expand that out, we're going to get a times a squared, plus a times b times I for these two terms, and then minus a times b times I for the other term. And then we get a minus b squared and an I squared. Again, the I terms, the purely imaginary parts, are going to cancel and go away. And we're going to use the I squared equals minus 1 here. And we're going to end up with a squared plus b squared. So the nice pattern that we see here is that a plus bi times a minus bi is all real with no imaginary component. And there's a secondary property that's maybe a little less obvious. If we just started with one of these, a plus bi, say, and you think about what we get when we multiply by the complex conjugate, so take a complex number and multiply it by the complex conjugate, you get a squared plus b squared. So the two components of the original z, well, that is the length or the magnitude of z squared. So that's a fun relationship you'll find in an intro complex analysis class. If you take a complex number and multiply it by its complex conjugate, you get an all-real property that's actually the length squared. So it's sometimes a handy trick to have available. And so that's super handy for a lot of things we are going to want to do. The form is straightforward in the Cartesian. The form is also straightforward in polar form. We just reverse the sign of the angle as well. And we have those two properties about the sums and products. So we'll see that appearing at various stages through the last week of the course.